Thank you very much. So the answer to the question of the conference is, of course, why not? However, I should apologize. There won't be any category theory and there won't be any physics in this talk. But nevertheless, everything expands into category theory and expands into physics. But I'm just going to focus on the kind of the nugget of it without all the complications of proper category theory or proper physics. Okay? And I want to address this question, which was the motivation when I was doing my PhD thesis. So if Boolean algebra is the simplest theory of physics, where you classify things into containers, give them names, it's a kind of theory, what happens to Demorgan duality? So of course everybody knows you take a subset and you replace it by its complement, you interchange and and or, zero, empty set and everything, etc. Now the heuristic idea is that this wouldn't be possible in quantum gravity, in just in ordinary physics. This would be lost because apples curve space and not apples don't curve space. But it could perhaps be restored in a theory of quantum gravity. So in a theory of quantum gravity, one person might say this person is, where you've got both quantum theory and gravity, one person might say this space is as full of apples as GR will allow. And if there's a maximum density you can have from the point of view of GR, because if you try to put more apples in, they'll just expand the black hole. Or another person could say, no, in the same situation, kind of the same effect, but use a different language. So there's this like kind of, this Demorgan duality is not changing anything, it's just a change of, well, it doesn't sort of change what is true. It's if you do it in a propositional logic context, then it means that if A implies B, then not B implies not A. It's the same thing, it's just a different language. So in this other language, somebody would say not apples, it's as empty as not apples as something would allow, and that something ought to be something like quantum field theory, where you have vacuum fluctuation, so it can't be completely empty. So this is completely heuristic, and you shouldn't take it too seriously. But it's a motivation. And so at the time, I couldn't go in that direction. I didn't know how to do it. So I went a different direction. I talked about sort of it suggests a dual relationship. And I interpreted that as a representation theoretic self-duality. And this led to Hopf algebras, a kind of observable state duality. The dual Hopf algebra is another quantum system. It's the other people. Person A thinks that the algebra is the observables, and person B thinks that the co-algebra as an algebra is the observables. So it's a kind of observable state duality. This led to Hopf algebras, and this was the origin of the less famous class of quantum groups, not as famous as the Drinfeld ones, but they were new quantum groups at the time in the 80s. Now, this idea obviously fits into logic in some sense, if you believe the intuition. So, so we know that logic, quantum logic, is somehow intuitionistic. There's some kind of Heiting algebra usually in the background. Logic, according to this, then, gravitational logic. There's some typos there. Gravitational logic should be co-intuitionistic, which also fits with ideas of Bill Levere. So my example that I do here is Schrodinger's cat is neither dead nor alive, because there are things that are in between. So the co-Schrodinger's cat, when you have a cat falling into a black hole, yes, the cat does die in a finite proper time, gets crushed by the singularity. But from the point of view of an observer at infinity, the cat just hovers on the horizon, never dies. So the cat is both dead and alive after sufficient time. So to my mind, this is like a flavor of co-intuitionistic logic. Of course, don't take it too seriously, it's just for fun. But then so is Schrodinger's cat, I think. Now, from the point of view of duality ideas, the way I did it at the time was you can sort of organize mathematics where one half represents the other half. This leads to a vision of reality as grounded in itself. Half of it represents the other half of it. And so the self-dual axis would be self-dual things, and I put Boolean algebra there, but with a big question mark. They don't really know how it fits in with the other dualities. But over here, monoidal functors, they actually are self-dual category, and that's one thing I proved it shortly after my PhD thesis, was that you have a dual notion of a monoidal category when you have a functor. This is now called the Drinfeld double, but that was in my work from then. So now there's also physical motivation. So you can think that black holes, because of the black holes no hair theorem, they are in some sense very primitive, simple objects. They just have mass and spin, an electric charge, just similar to elementary particles. And there's a kind of duality between them. Just all I'm going to say about this for now. So now I want to address this, but I'm not going to do physics or category theory. Instead, I'm going to, that's a huge mountain. Quantum gravity is like a mountain. Instead of trying to climb the mountain, I'm going to bring the mountain to the problem by looking at this issue, but using the modern tools. So 30 years later, motivated by all of what I've just said, and by other people with other motivations, we now have a fairly good understanding of some kind of quantum Riemannian geometry. And so I want to apply that to Boolean algebras and see what's true. And I should warn you that my vision, won't exactly be realistic. The models I'll show you are too simple, but you get an inkling of what I wanted, maybe. You can judge. So the data for quantum Riemannian geometry is going to be an algebra, a space of differential forms. So the algebra is like the topology, the topological space in some sense. The differential forms are like the differential structure with an exterior derivative. Then there'll be a metric and a connection and a curvature and all that. So there are various approaches, but I'm going to use a very constructive approach, which is based on the fact that the space of differential forms are a bimodule. You can multiply them from the left and the right. And this has sort of been expanded over the years, developed over the years, and it is now appearing in this book. So that's a little plug for that, which you can order already. This approach is very different. I'm just kidding. I mean, you can order it, but you won't get it. Different from Kahn's approach. Different from algebraic geometry, also different from synthetic differential geometry. It's just different. We don't have toposes, we don't have open sets, we don't have pre-sheaves, we don't have any of those things. But instead what we have is something that works globally, and it works over any field, including a field of two elements. So we're going to apply this to the power set of the set of subsets, and we're going to extend Demorgan duality to differential geometry. And just treat this as a bit of fun. This is, for me, this has just been one massive exercise. It took me longer than it should have done, but it's been basically an exercise. We'll see how it extends to metrics, connections, and curvature. I will show you some examples. These examples come from a paper with Anna Pachol, who's Polish. And we have a program of classifying quantum Riemannian geometries over F2. We call them digital geometries. And we have a paper in JPhys-A, so that's where I'll draw the example from. In some form, there's quite a lot to convert it into the current form, but ultimately it's there in the classification. Okay, so first step. So the program is explain the formalism a little bit, explain how extend it to sort of apply it or specialize it to power sets, and then explore this connections. So. Differentials on an algebra. So of course, the algebra you could keep in mind is C infinity of M, which are really the zero forms on a manifold. They're part of the exterior algebra, which is a differential graded algebra. We're going to focus mostly on the one forms and the two forms. So the one forms, they would be something you can multiply by a function from the left and the right. Of course, classically they would commute. And you've got an exterior differential which turns a function into a one form. This is how it does it. So in a local coordinate system. Of course, this is local coordinates. This is defined abstractly, universally. Now, of course, there's a wedge product to multiply forms, and D extends obeying the graded Leibniz rule, and classically it would be supercommutative. Now, what we do is, for non-commutative geometry, is we let the algebra be any algebra over any field. We drop the graded commutativity, so we drop this in particular. But we keep that there is some bimodule omega 1 of one forms. And bimodule you can associatively multiply from either side. And we keep that there is D obeying the Leibniz rule. We keep that omega 1 is spanned by things of the form ADB. And to not make sure we're not doing something silly, we tend to demand this optional condition that the kernel of D is just a constant, which is connectedness. Now we want this to extend to a differential graded algebra, so we'll take products of one forms and quotient by some ideal. Now, the one thing that's very unusual, all of that is fairly straightforward. We've just let go of the commutativity axiom. The one thing that I want to emphasize, which doesn't happen classically, is that typically, because because D is a graded derivation, when things are very non-commutative, derivations become inner. So you can actually expect that in quantum geometry, the more typical case is that there will be a one-form theta whose graded commutator generates D. This could never happen classically because this right-hand side would be 0 classically. But in the quantum world, that is actually the typical situation, not the atypical situation. So we live in a world, the geometry as we know it is an extremely singular point in the variety of quantum geometries. It's just, it has a number of things where you don't see the full structure. Okay, these diagrams were for Bob, but he's not here. Given a differential structure, a metric is just a 1-1 tensor, a tensor with two lower indices, if you like. It should be symmetric, so we say that when you apply the wedge product to it, you should get 0. It should have an inverse, which is the inner product metric, and they should be inverse in this sense. So that says that omega 1 is an object, is a rigid object in the category of A bimodules. The unit object is not a number, but an element of the algebra. A connection, connections algebraically go back to Quillen, Karoubi from the 70s, a left connection. So that would just be a map from omega 1 to omega 1 tensor omega 1. Now, normally you think of a covariant derivative, but if you have a vector field, you can just evaluate against the first output. So this is like a coaction if you do quantum groups. You evaluate against the first output, and then you'll have an actual operator, which is a covariant derivative. But we can have to specify the vector field itself, so abstractly the connection is a map like this. And it should obey the covariant derivative Leibniz rule from the left. But what happens from the right? Because we have bimodules, we want something from the right. So from the right, we do the same thing. We have omega tensor df, and we have nabla omega f, the same like this. Except for one problem, the df needs to be on the left where it will connect with the vector field. For this to be consistent, the vector field will always appear on the far left when we evaluate it. So we have to flip sigma. We have to have some map sigma that will flip the df with the omega. And classically, it would be the flip map. Now this is not extra data because it's determined by this equation. So it's just that some connections will admit such a map and some connections won't admit such a map. If it does, it's called a bimodule connection. This goes back to Peter Michaux and Dubois-Violette. So, and one or two others. So now, the advantage of having a bimodule connection, well, we're having bimodules and a bimodule connection, is that you can tensor product bimodules, and this connection will extend to tensor products. How will it do it? Well, the connection will act on one, and then it will act on the other, and then the leftmost output, the left output of nabla has to go to the far left to evaluate like these would with a vector field. So we need sigma to flip them over. So here it is applied to the metric. Metric is omega 1 tensor 1. We apply one, we apply it to the other, then sigma will take the output of nabla that connects to a vector field, will take it to the far left. So, so nabla metric compatibility is that nabla G is 0. And so that is all very natural and makes perfect sense for any algebra with differential structure. We also want zero torsion. What is torsion? Actually, torsion is just, there are two ways to go from omega 1 to omega 2. One is to apply the exterior derivative d, and the other is to apply nabla and then apply wedge. So the nabla goes into omega 1 tensor omega 1, and then we apply wedge to it. So this would be, so you would never see this in geometry textbooks because they don't. But this is what's happening. If you're an algebraist, different geometry is really straightforward and easy. Torsion is just this equation, and curvature is a map from omega 1 to omega 2 tensor. The reason why you evaluate curvature on a pair of antisymmetric pair of vector fields is that really it's an element of omega 2. Again, that's not obvious if you look in ordinary geometry books, but that's what's really going on. And connection is really a map like this, and it's just defined as you apply D, you apply nabla, and then you apply D, and then you subtract nabla squared. Or more precisely, this is the curvature, and you subtract this to make it tensorial. So this is then a left module map. So everything works, and you can improve things like the Bianchi identity. You can improve at least some of the Bianchi identities. You need a bit more structure to prove some of them. The Ricci tensor is where the book sort of runs out of steam. We have an idea which we use in the book, but I don't have a truly convincing idea. The reason is that I don't know, and I don't think anybody really knows, what the Ricci tensor really is. Right? In physics, we tend to use a certain contraction. You just take the indices of Riemann and you contract two of them. But what's that, right? So I don't know, so I just contract indices. So where I contract indices is I take the metric. I'm living now in omega 1. I apply the curvature. I'm living in omega 2 tensor omega 1. And then I need some kind of map to undo the wedge product. So a map I to go from omega 2 into omega 1 tensor omega 1. So classically, that would just be the map which replaces the two form by an antisymmetric antisymmetric pair of tensors, a combination of tensors. So we take that map for granted when we do tensor calculus, but it's there, and we have to express it because we don't know what omega 2 looks like. So then, now we've got omega 1 here. We can complete the trace. And so that is let's call that the naive Ricci tensor. And that's all we have at the moment. I would love to have a better Ricci tensor, but that's what we have. Once you've got the Ricci tensor, you can contract it further, take another trace, a cup at the bottom, and that will give you the Ricci scalar. And all I want to say is this depends on I. So now you've got to analyze all the possible i's whenever you compute the Ricci tensor, which is a bit of a pain, but okay. All right, so that's the formalism. Here's an example. Which might be relevant to quantum computing, to the two-slit experiment, or two-state quantum system. So here the algebra is 2 by 2 matrices. You can classify all the possible differential structures. There are 3 types of them, depending on the dimension. So as bimodules, they could look like that, or like that. The one we're interested in, let's say the two-dimensional ones, so that looks like a two-manifold. And then you can analyze what are all the possible D's, exterior derivatives, and they turn out to be labeled by the moduli of them as CP2. So basically, the D has the form dA is the commutator with some matrix times the basis element for this copy, plus some other commutator with another element times the basis element for the other copy. So that's what dA looks like. You could write direct sum if you want. But some of these will be isomorphic to some others, so they will actually only have a CP2 worth if you look at it up to isomorphism. So that's the moduli of differential structures. And so here's a concrete example. We'll take these to be E12 and E21. So these are the off-diagonal 2 by 2 matrices. And so the differential is a partial derivative where you commutate it with the upper triangular bit and the other basis element, and the other partial derivative is the other corner. When you look at the exterior algebra, you need to impose some relations in degree 2, and the natural ones turn out that they have to actually commute rather than anti-commute. It's a bit weird, and you can impose these ones that square to 0. So then you've got omega of the dimension of a 2-manifold. And once you've specified omega, you've got obviously a cohomology for that. This is the quantum de Rham complex, and this is what it looks like. So it looks a bit like a torus, in fact. Okay, it has a top form and has has Pontryagin duality. Now for the geometry, I take the simple any 2 by 2 matrix in a basis ST will give you a metric. It will fulfill the axioms that I talked about, any invertible 2 by 2 matrix. So I'll just take the simplest one, Euclidean metric. You can analyze it, and you get a 3-parameter moduli of Q of quantum Levi-Civita connections. So the theorem that says that there's a unique quantum Levi-Civita connection, that is very special to classical geometry, to the classical setup. It isn't true if you change the Lie group classically. It isn't true if you're in the quantum world. So there's a 3-parameter moduli of them. I've just given one simple one as an example. And in this example, sigma is basically the flip map, but it's got some weird signs. And the curve, I like this example because it's very simple, but it has curvature. And the curvature is given by this Pauli matrix, sigma 3. The Ricci tensor is again given by this Pauli matrix for this lifting map. Okay, so that's the end of the introduction. More or less, of the formalism. Now I'm going to start moving to what we actually need. We're going to be looking at discrete spaces. So far the field is still general. So fx is a discrete space. I'm looking at the algebra of functions on x with values in the field k. And omega 1, you can analyze what they are, and this time they're classified by graphs, directed graphs, whose vertices are x. And so omega 1 is literally the span of the arrows. I'm using graph in a strict sense. There's only one arrow, at most one arrow between any two vertices and no self arrows. Then omega 1 is the span of the arrows. You can say it has a base label, but literally it's the span of the arrows. Now, the bimodular structure is if you multiply an arrow from the left, you pick up the value of the source. If you multiply an arrow from the right, you pick up the value of the target, the location of the target. And the differential is just the difference across all possible arrows. So it's very natural. It obeys all the axioms. There is an it's inner, so this is the inner element. It's the sum of all the arrows. So this would require the graph to be finite, the x to be finite. G, a metric, is an element of omega 1 tensor omega 1. But for reasons which are not obvious, it turns out that this final arrow location has to be the same as the source location. So this is a fact, you can prove it, that it turns out G has to be of this form for some coefficients. And that requires the graph to be bidirected. It has to be an arrow both ways. And these are non-zero metric lengths, or directed metric weights of some kind. And the canonical choice, which we're going to focus on, is just the Euclidean metrics. So you just take one everywhere for all the weights. Now, the last thing I have to specify is the exterior algebra. And I'm going to just let it be generated. So there's no very good answer. In general, if I've got omega 1, there is always a maximal universal exterior algebra you can generate from it, but that's generally too big. This one I call omega min, but it's not the absolute minimum. These relations might not be enough. You might want to add some more, depending on what you were trying to model. But this is a canonical choice. And you just add in all these relations. You fix x and y. For every x and y fixed, you look at all arrows for all z's in the middle. And you just set the sum of those to be 0. And then the d you extend using the fact that it's inner, you extend it like that. So that's what we'll do. But we will do it over the field F2. So we'll take a Boolean algebra, atomic Boolean algebra, and we'll just regard it as functions on a space X with F2. And let's just take X to be finite to keep it simple. So I'm stripping away all the fun bits if you're a category theorist, but this is the bit that we want for geometry. So we're going to work with a subset. So P of X is the set of subsets. A is a subset of X. And omega 1 is going to be spanned by the arrows, but actually you can think of that also as subsets of arrows, because a vector over F2, if you've got a basis, which is the basis of arrows, then a vector will just be some coefficients in the basis, and either there'll be a coefficient or there won't be a coefficient. So again, it'll be another subset. So vectors are again subsets, which will be the power set of the set of arrows. And we're going to fix a differential structure on X, so that we have a Boolean algebra plus choice of differential structure specified by a graph on the vertex set. How you would say that in logic, I don't know. I mean, some sort of, a graph among the propositions, among the elementary propositions. So bimodule products, what do they look like in set theory terms? So this is now an exercise. We're converting the axioms, the example I showed you previously, but specializing over F2 and converting it into set theory language. So what you get is you get an intersection of an arrow of a subset of X with an arrow. Namely, the intersection of a subset with an arrow is all the arrows in omega whose tail, that's the beginning of omega, is the tail of omega, and that has to intersect A. So tails lie in A. And on the other side, the right part of the symbol omega is all the heads of omega, all the tips of omega. So this means the arrows in omega with tip in A. So it's a very intuitive notation. Now D turns out to be all the arrows which cross the boundary from A into bar A into the complement of A. So they're the finite differences with non-zero finite difference, if you like. So that comes out to be this. So they're the arrows that cross from the interior of A to the exterior of A in a Venn diagram. I mean, no such thing, but in some sense. And you can check, it has to, because it's part of the theory for any field, but it obeys the Leibniz rule. So the D of intersection is the exclusive OR, that's the plus symbol, of dA intersection B plus A intersection dB. So that's the Leibniz rule. And so it's expanding out the exclusive OR, that is A or this, and not both of them. Okay, here's the Venn diagram proof. We have to prove this is true, but we can just prove it anyway for fun if you were teaching this without knowing the preceding theory. This is X, here's A in black, here's B in red. Let's look at, let's say, the black arrows. They are dA. So they're all the things that cross the boundary of A, but I put all possible flavors of them, depending on where they end up. But they all cross the boundary of A. And similarly, the red ones are all the boundary of B. They cross the boundary of B. And now I'm going to intersect them. So the A intersection dB means the ones whose tails are in A. So that's these. Well, these, including that one. And for B, sorry, that was for B. That's A intersection dB. And for dA intersection B, it's the tips have to lie in B. So that's these. And now we have to exclude the intersection, the one that's in both of those. And so that's this arrow here. Because that's in both. That's both a red arrow and a black arrow. So we exclude that. And that, now if you look at what you've got, then you've just got that box and that box. But then you exclude, I didn't say that very well. You exclude, they're not even counted. They're not even, sorry, I didn't say that right. These aren't even counted. We're looking at these arrows and these arrows, but this one is in both. This one and that one is in both. So we exclude those, but they're not in the green box. So the green box are what you have left. And those, if you look at it, are exactly the arrows that cross the boundary of the ellipse of A intersection B. So that's how it works. Now, what about the metric? The metric has to live in omega 1 tensor omega 1 over P of X. So if you think about that, well, when you wedge product, when you tensor product them and convert it into set theory, what you're doing is you're looking at arrows which concatenate. So omega tensor eta is just a set of two-step arrows, where the one step is in omega and the other step is in eta. Omega and eta are subsets of arrows, because they are elements of omega 1. And this gives you an element, a two-step. So this is exactly the power set of the two steps. Arrow 2 means the two-step arrows. And so for an example, an element in there is the metric. And for a graph with only value 1 on every edge, because we've only got two elements and we can't have 0, Euclidean metric, this is the metric, then that's fixed. So it's a sum. It's a sum of elements. So sum means direct sum. That means exclusive OR. And it's a sum. Each element is a subset of the set of two arrows. It's an element here. So, and these are the subsets. These subsets are the subsets where I hold P and Q, the ends fixed. I described that already. Now, omega 2 is, the two forms are going to be a quotient of omega 1 by the ideal, that, which I had mentioned. I think I mentioned it. Yeah, so that relation that I showed you before, that what you're really doing is you're quotienting by an ideal where you keep the ends fixed and you allow everything in the middle. So what you're doing is you're quotienting by, so this will now be a set, and what you've got here is an equivalence relation. And the equivalence relation is that two things are equivalent if they're related by, by an element here, and this is the subset. Each of these is a subset of the two arrows where P and Q are held fixed, and a collection of them means therefore a set of elements of omega 1 tensor omega 1, and we're quotienting by them. Okay, d omega just turns out to be the same idea. It's the two steps where the first step, one step of the two steps is in omega and the other one isn't. So it crosses the boundary of omega. So here's the collection of arrows, omega, and the two steps where one half of the two step is in omega and the other half of the two step is not in omega, they are things in the boundary of omega. So it's exactly the same idea as we had for, because after all it's the same construction. The arrows are the power set, but now it's the power set of the set of arrows that we're interested in. But then arrows also have a kind of graph structure inherited, which is that xy has an arrow to y z if it's composable. So that's so we're using that graph effectively. There's a kind of two category or probably an infinity category in there somewhere. As you iterate this construction, well, it said that our things will usually terminate. They don't have to. Okay, now, so that's all the geometry of the exterior algebra. Now, Demorgan duality. So now, A bar is going to be what I call P bar of X. So everybody knows that P of X power set has a ring structure, but people don't usually think about this other ring structure, which it equally well has. The product is the union, and the addition is the exclusive and, rather than is the inclusive and, rather than the exclusive or. So it's just the De Morgan dual. So it's A intersection B, or not A union B. And if you work it through, that actually is the same thing as the complement of A exclusive or B. And that relies on the fact that exclusive or doesn't actually see complementing both its arguments. So this inclusive and, it is what you would get if you do exclusive or and convert back using bar, which is obvious because it's the De Morgan dual construction. So that's the algebra P bar. And now we take for omega 1 bar, we take P bar of the arrows. We've got the same graph, but we take the De Morgan dual. And so now this time the bimodular structure is you take the union of an arrow with a subset, which are all arrows in omega or with tail in A. On the other side, it's all arrows in omega or with tip in A. I should say that these extensions of intersection and union to arrows are non-commutative, right? That is not the same as that. Similarly on the other side. So this is a non-commutative extension of set theory. It's inner. Now, what's really cool is that the inner element is the De Morgan dual of the other inner element, but the other element was all arrows. So this is zero arrows. This is the kind of duality I was talking about. Everything on one side becomes nothing on the other side. So one person uses, so what is for one person the empty set becomes a thing that generates the derivative on the other side. It becomes, it is not all arrows. It is literally the empty set. But for the rules I specified, you can check that the empty set union A, inclusive and A union in union the empty set, well that doesn't do anything, so that would be just arrows with tip in A, and these would be arrows with tail in A, but it's the inclusive and, so that comes down to wholly in A or in complement of A. So that is in fact, so we're going to call, and that's the differential that we have. It's arrows that are wholly in A or wholly in complement of A. In other words, they are not crossing the boundary of A. So, so this all fits, and you can do a dual proof by Venn diagram, but I don't think I'm going to have time to read through it. So, what's that? Yeah. Well, okay. So, okay, I'll say it very quickly. So, same thing. We take the black arrows here are D bar A union B, and the red arrows are the other side. And what you do is you just compute all the possible, you write down all the possible types, all the possible flavors. That's what you do for Venn diagrams. And you just and then all the parallel ones are the ones which are the intersection. So that one would not be an intersection, but that would be intersection, that would be intersection, etc. But then we have to add in an arrow that's not in the union. But if you count them all up, there's one flavor of arrow that's left, which is not in the union of all these black and red arrows, and that's this blue arrow. So you throw that in. When you add that in, you look at it, and what you've literally got is all the arrows that are wholly inside the union or wholly outside the union. So that is exactly the boundary of A union B. So it obeys this Leibniz rule. Okay. We just have to finish this job a little bit. It's a little bit, you can sort of guess the rest almost. But what is the opposite of concatenation? What's the co-concatenation of two arrows? Okay. So if you've got two arrows, two subsets of arrows, omega and eta, then we define it to be the two steps where one step, the first half of the two step is in omega, or the second half of the two step is in eta. And I figured that out because I went to the dual side. I took the complement of omega complement concatenation eta complement. So this is then required for it all to work. And this is very natural. It's kind of replacing so concatenation is a kind of intersection of the tip of one with the tail of the other. And this is the kind of union. And then omega 2 is going to be a quotient of this cotensor product divided, I mean, it's a tensor product over this algebra, but I can call it cotensor product, but it's actually a tensor product over this algebra, divided by some ideal. And this ideal consists of these, or bimodule, sub-bimodule, and this consists of these elements here. And they are the same as before, but now with the inclusive and instead of exclusive or. And then you can check the D extends to this. So D is now two steps which are wholly in omega or wholly out of omega. So like that or like that. And so this is the same construction as we did for P bar of X. And this time D is given by the commutator with the bar product of the zero element of the empty set. Then there's a lemma that these constructions are all compatible. And what it really boils down to is that because where you constructed it, the Demorgan duality extends to the intersection and union of arrows and subsets. And so because of that, and because of the way that d bar was defined as complement of dA, this diagram commutes. And this map bar is a bimodule map with respect to the relevant products on both sides. So this is what we would call, in the algebraic language, we would call this a diffeomorphism. And this extends to the higher levels. So I've written it here for this, but the two arrows are the next level up. That's omega 2, etc. So what you get is a diffeomorphism. Okay, so we have extended Demorgan duality to differential calculus. Now I'm going to close with an example. We're going to look at quantum Levi-Civita connections on a polygon graph. I have been studying polygons with a student in Queen Mary, but this is not that work because we're only going to look at a very trivial one. What we've done is the students look at arbitrary metrics and solve the equations. But here we've only got the Euclidean metric, which is trivial to do. So I'm just going to show you a trivial example to start with. But the zero metric, if you like, zero connection. So anyway, so omega 1 is going to be. Before I do that, I've got to explain one little lemma from the general theory, which I haven't told you yet. When a calculus is inner, which it is in our case, then connections, bimodule connections, are totally specified by two bimodule maps. Sigma, which you knew you had to have anyway, and alpha, which is any bimodule map from there. So then the connection is of this form, and conversely, every bimodule connection will be given by this construction. So classification of bimodule connections is really easy. It's just a pair of bimodule maps. In the inner case. That's not obvious. I'm not going to show you the proof. Now, then you check when it's metric compatible, and that's got to be compatible with a metric, so this is the condition. And sigma 1, 2 is just mean apply it in the 1, 2 position of the tensor product. And torsion free comes down to this condition. So in terms of alpha and sigma, these are the conditions for a quantum Levi-Civita connection. Okay, so you're going to take that on faith. I haven't got time to show you the proof of that. Now we're going to apply it in our case. So in our case, we're going to be looking at arrows, maps alpha from power set of subsets of arrows to subsets of two steps. And sigma is a map from subsets of two steps to itself. And because I'm going to, it's not necessary, but it's quite convenient to organize the polygon to label them by the group Zn. And then you can look for left invariant one forms. if you've ever done any real differential geometry on a group, it's far, far easier to do it in a basis of left invariant one forms than it is to do it any other way. So, so we just choose the basis of invariant one forms and what they look like with respect to the Zn structure, cyclic rotation. So they look like this. This is a one form because it's a bunch of arrows. It's all the arrows in one orientation, all the increasing arrows. And E minus is the subset of all the decreasing arrows. And they form a basis. So given any arrow, any collection of arrows, I can define these subsets, which are the tails of the positive part of omega and the tails of the negative part of omega. And then I can reconstruct omega in this basis. So they form a basis of left invariant one forms. And then I've got to tell you what the exterior algebra looks like. So going through that universal construction for any graph, that construction, but it only gives the right answer for n not equal to 4. Then you obtain these. Well, these are what the subsets of arrows, two steps with endpoints fixed look like, and I'm setting all of those to 0. That's omega 2. And in algebraic terms, what I'm doing is I'm assuming that these commute or anti-commute, but there's no minus sign, and that they square to 0. So this is like the Grassmann algebra on the left invariant one forms. The metric I told you was canonical anyway. It's given by all the things of this type because they have to go and come back to the same place. So that's the metric. And you write down these things, and then you can check, and you write down this sigma. And sigma is just going to, so this is actually a partition of the two arrows. So by specifying sigma on each component, I'm specifying sigma as a map, as a bimodule map. And what it does is it swaps, when it acts on this component, it just swaps the two entries, because these are all two component sets. And on these, they're just the identity, nothing else you could do. So that's sigma, and you can check then at the basometric compatibility conditions. Now, what does the connection look like? So in algebraic terms, it's just that the left invariant one forms are covariantly constant. But in our set theory language, alpha is 0, and nabla is a map from omega 1 to omega 2. So it sends a subset of arrows to a subset of two steps. And what that subset is, well, I first split omega into its two components, positive part of omega and the negative part, increasing and the decreasing part of omega. And then each of those has a boundary. So d plus omega are all the points I where the tail, with a tail in omega plus, but the one before that is not in omega plus. Or the other way around, the head is in omega plus, but the one after that is not in omega. This should be a plus here, omega plus. Similarly with a minus. And then at each of those boundary points, I'm going to associate this particular one form. And that'll be, so then I'll sum over the boundary points, and I'll take that particular one form, and similarly over the negative boundary points, and I'll sum over that. So I'm going to show you a picture, you'll see what I mean. So this is the positive part of the trivial connection. Here's omega in the grayed box, omega plus, part of it, half of omega. And I look for the boundary points. So the boundaries are just ones on the edges. So the white circles are the boundary points. At each boundary point, I have this combination, which I called EI plus. It's a backward form and a form like that, a two form like that. So that's it. And similarly on the minus side, and you can check that it obeys all the requirements. It's a nice checker with some of this, well, you can say with Venn diagrams, and G and R, and the curvature is 0. Now, for n equals 3, I happen to know what to expect, what the full answer is, because there is a classification by computer with Anna Pachol in this paper. That, so there we found that for n equals 3, there is indeed the trivial connection. So this is just this connection here. I spelled out some examples. But there are 3 other connections. So 2 of them, quantum Levi-Civita connections. So 2 of them, 1 and 2, are flat. So all 3 of these are flat. So this is the 0 connection plus an additional bit, which looks like this. It's associate this particular 2-step or particular 1-1 form to all the points which are tails of omega, of the positive part of omega. And similarly for the other side. So here's an example. The last one I'm not sure it's how illuminating this is. It's just showing the calculation. Nabla omega, the third one, has both pieces. It has this piece that we had before and this piece that we had before. And this time there is curvature. So there's a unique quantum Levi-Civita connection with curvature and 3 quantum Levi-Civita connections that are flat. And the curvature is it's an operator from 1 form to omega 2 tensor 1 form. So the volume form is the top 2 form. I didn't discuss that in a lot of detail, but it's there. And omega is an arbitrary subset of arrows, 1 form. Now the Ricci tensor depends on the lift, but from the paper with Anna, we happen to know that there are exactly 2 lifts for which the Einstein tensor, defined like this, is conserved. What this means is you apply nabla, and now you will live in omega 1 tensor omega 1 tensor omega 1, but then you apply the Ram bracket in a product, which gives you an element of omega 1, and that's to be conserved, that's contracting, if you like, so you want that to be 0. That's a reasonable thing to ask. What's a bit unreasonable is this one. Normally you would have this formula, but you'd have 1 over n here, for n was the dimension of the manifold. But we don't know what n is, and particularly it can't be 2, because 2 doesn't exist in our field. So the only thing you can put here is either 0 or 1 for the coefficient. So this one fits with a 1 here. And so then there are exactly 2 lifts that do that, and they're very natural. This is the lift, just the sum of all the positive arrows that go out and come back. And this is the other lift, is to go back and then go the other way. So there are 2 possible lifts. They both split the wedge product. So if you apply wedge to it, you get back to the volume form. And then the corresponding Ricci tensors are like this. Okay, I'm not sure. And what's maybe the thing to carry away from this is the Ricci scalar is 1, so it has a constant curvature. Now the Demorgan dual connection. So I'm going to define the Demorgan. So firstly, the thing to observe is that nabla 0 of the direct sum, exclusive OR of omega and its complement. Well, that's everything. So that's theta. But that just turns out to be 0, the empty set. So another way to say that, so what that means is that if you define nabla bar, which is the De Morgan dual connection on P bar of x, you define that as the bar of omega, then you apply nabla 0, and then you apply bar to get you back. So this would be the natural De Morgan dual of the previous nabla 0. But then because of this property, that just gives you back the complement of nabla 0 omega. If you do that for the third connection, the one with curvature, it's a little bit more complicated, but you get something similar. Instead of you do this calculation, what applying the complementation does to omega. It generates this. Then when you go through that definition, you define this as the De Morgan dual of this nabla. Then what you get is you get the connection 3, but then you're adding the metric to it as a subset as an element of omega 1 tensor omega 1. You go through the dual construction for the curvature, and it's a nice check. You do get the expected answer, which is the De Morgan dual of the previous curvature. This is what you should get, because this De Morgan duality was a diffeomorphism. So it shouldn't change anything ultimately. It's really just a change of coordinates ultimately. But it's quite a lot of work to check that that's what happens, but it does. Okay, I'm just going to end. I'm probably supposed to stop very soon, right? 50 minutes, right? So I did begin 5 minutes late. So I'll stop very soon. So I'm just going to do one remark, is that how generally, I've done a very specific thing. What about other algebras over F2? Well, actually, it turns out it can do the same thing for any algebra over F2. So I can define A bar to be the same set as A, but with a new addition law and a new product. And this is totally bizarre to me anyway. The 0 of the 1 of the original algebra becomes the 0 of A bar, and vice versa. So this is like De Morgan duality. Of course, these algebras are ultimately isomorphic. What I've done is I'm changing A to A bar, which is 1 plus A. So this is what would recover De Morgan duality for the power set. You can also check from this definition that A times A with the modified product is actually the same as A squared. So that means that the algebra is Boolean if and only if the original algebra is Boolean. So this construction preserves Boolean algebras. And this is just an exercise, a fun exercise. But what you can do, which takes a bit more work, is you can extend this to differential structures. So if A now has an exterior algebra, so a differential graded algebra, and you pick some element theta, which as far as which is arbitrary except that I require it to be closed. So one form that's closed. Then you can define omega bar as a differential graded algebra structure on A bar, and I define it to be the same vector space as omega, but with a modified addition law where I add in theta. Instead of 1, I've now got theta. And the modified left module structure and a modified right module structure and a modified D. And that's in degree 1, omega and eta are degree 1, and this is in degree 2. Etc. I didn't actually, in the paper I should say there is a paper which I'm going to put on the web. I just finished it for this conference. But I'll put it on the web this weekend on the archive. And I didn't bother going higher degrees, but the same thing works in all degrees. And omega bar is inner using, if theta is the inner element, doesn't have to be, if it generates, makes omega inner, then theta bar makes omega bar inner, but theta bar is the 0 element of omega. So the 0 element of the bimodule makes omega bar inner. So it's got all the flavor of the Demorgan duality. Okay, and last slide is just to apply it to an example of a non-Boolean algebra. So a non-Boolean algebra over F2 is, for example, the group. So this is actually the dual Hopf algebra. So the example I did before for the triangle is actually, I identified it with Zn, so it's actually functions on Z3. And this is the dual Hopf algebra. So this is like in keeping with my philosophy of duality. This is also of interest, but it's not the De Morgan dual, it's the representation, the Hopf dual, A bar, of the previous example. Now, because in this paper we classified all quantum geometries, digital quantum geometries up to dimension 3, it has to be in our list, so it is. And so this is read off from our paper. So the algebra has a generator x cubed, which x cubed is 1, that's Z3, the group algebra of Z3. I take a basis, a rather naive basis. There are cleverer bases you can take, but in the classification we just took the computer-generated basis, which is omega 1 is dx, omega 2 is dx squared. And then you have various commutation relations. This counters is inner with this element. And the exterior algebra, when you go through the construction, gives you this. So you can see that it's a little bit weird. They give you 0 and these give you, well, it's this relation. But the point is it has a top degree. So so the dimensions are 1, 2, 1, just like a 2 manifold, just like the previous example. But theta squared is 0. There are 3 natural metrics. They're all multiples of G0. And each of them has 3 flat connections and 1 curved connection. It's very similar to what we had in the other model. Remember, we had 3 flat connections and 1 with curvature. We have the same thing here on the dual model. We have 3 flat connections and 1 with curvature, but for each of our 3 metrics. That's the only difference is there we only had 1 metric, now we've got 3 metrics. And so these are the 3 curvatures. There are 2, just as before we had 2 natural lifts, here we've got 2 natural lifts. And these are the Ricci tensors. Now, what about De Morgan duality? Well, you apply that weird construction, and then you see, so if you compute x bar dot x, etc., see what relations it obeys. It obeys exactly the relations of y, which is 1 plus x. And you just have to identify a change of basis of your other element as well. So omega bar, the new basis would be theta plus omega I. So bottom line is De Morgan duality is actually just, at least in these examples, is actually just a change of coordinates. And that's good. So the philosophy that, so these are my concluding remarks. We did see De Morgan duality extended, but it only worked because we had a quantum geometry. It's of course a toy model. It's not real quantum theory, not real gravity, but we saw some of the flavor of what we wanted. It's non-commutative because of this. In the dual picture, things which are very prolific, like all the arrows, become the empty set, like no arrows. So that was the kind of philosophy that I wanted to espouse. Ultimately, this idea that physics should be Demorgan invariant gets subsumed as quantum diffeomorphism invariant, which is quantum version of GR. So that's good, I think. And I said this generalizes in different ways. Of course, you can try to generalize it to Heiting algebras, whatever. I don't know how to bi-Heiting algebras, but here we generalized it to other algebras over F2. Now, I want to mention that, of course, what I did. So that was the end of my talk, basically. But this was all like an exercise. There's a whole formalism you can apply to any algebra with any field. So this was just applying it to one very specific thing, topical for this conference. But you could, for example, take a graph, and you could have do it over R, and have real values. What's more, in the theory, the theory doesn't want you to doesn't ask you to have the same length of an edge going from X to Y as the reversed edge. So you could have a different length from A to B as from B to A. That is perfectly allowed by the mathematics. It would be rather weird for a lattice for embedding in Rn, but from the point of view of the geometry, it works. And I actually think this could be more relevant to probability. So you could think of this as like a transition probability, and then going the other way would be 1 over the probability. Something like that. You could take your favorite algebra, and the algebra could be non-commutative. Okay, so I'll stop there. Thank you.